Okay, this is category theory for idiots, and we're talking about products and co-products here. We start with an example. 2 classrooms. You're the principal. The first class is Mrs. Adams. And Mrs. Adams' class has Amy, Brian, and Carl. We're going to call this class A. The second class is Mr. Bond's class. That is Russ, Sophia, and Tom. We're going to call that B. Oh, I had to burp, excuse me. So again, we've got class A here, and we've got class B here. You're the principal, and both of these classes are going to be going on a field trip, okay? And you want the teachers to pair, you want them to pair up students like this. You want you want a student from A and a student from B. And this is going to be what our pairs look like. Okay? And the way that you're going to denote the set of all pairs is this. This is also called the Cartesian product. We're dealing with sets. And I'm going to pause the video for a second. I'm going to write down all of these pairs. Okay, so I've gone ahead and I've written down all of the possible pairs that we could make, where I've taken one element from A, and again we had Amy, Brian, and Carl in A, so you can see Amy paired up with every element of B, Russ, Sophia, and Tom. And then every element of B paired up with Brian, and every element of B paired up with Carl. Okay? And so you'll notice immediately there's 3 in this group, 3 in this group, and 3 in this group. And these groups, by the way, are Amy paired with someone from B, Brian paired with someone from B, and Carl paired with someone from B. Now, this is a total of 9 pairs. So for a total of 9 possible pairs. And we see, sorry about that, I keep coughing. I think we've all got the COVID here. So we can tell that the number of elements, and that's what I mean when I write these lines next to A times B, the number of elements here is just the number of elements in A, which was 3, times the number of elements in B, which was 3, which is 9. Okay? And kind of an important thing to note here. Okay, well, first of all, I should probably say this is the product, what I've just discussed. Pairs from A and B, okay? This is the idea of the product. Dang, okay. So I'm going to just write something. And I'll kind of explain this in a second. Okay. This is where you get into some of that mean-looking category theory type stuff. So again, this object, A times B, or rather, actually, I should probably change this at this point to A pi B, as that's the generalized product. In this case, it's the same as A times B. This is this object of all of these pairs, okay? So all of these pairs, the set of all of these pairs are A times B, or A pi B, okay? And the interesting thing, or one of the interesting things about this product is I can take this product and I can apply a map to it, pi A, and it gets me back to A. And I can apply, similarly, a map pi B that gets me back to B. So what the hell am I talking about? Okay, well, let's pick a pair here. Let's go Carl and Russ. I like both of those names. I'm just going to do Carl and Russ here. Okay? Well, pi A in this case of the pair A, B is who is in Mrs. Adams' class. What's the rule with this? When you have an S at the end of a name, do you just put the apostrophe after the S? Or is it Adams's? I'll put another S on there. Even that looks stupid, and I'm 30% sure that's wrong. Whatever. Who of this pair is in Mrs. Adams' class? That is the definition of this pi A. In which case, the answer is whatever A is. Right? That's who we created the pair in mind with. Right? We took an element of Mrs. Adams' class, and we paired it with an element from Mr. Bond's class. So in this case, pi A is just, in this pair, Carl and Russ, and again, I'll bring this set up here so you can see, Carl is in Mrs. Adams' class, right? So the answer to this question, who's in Mrs. Adams' class, is Carl, right? And so it's going to map me back to Carl. And we can see Carl is an element of A. And we also have that, this pair is an element of the product. Similarly, pi B is who is in Mr. Bond's class. And that's B, right? So from this pair, taking this pi B map, I get Russ. Woo. And we could tell Russ is in the set B, right? Now, why do we use the Greek letter pi for this? Well, pi is kind of like P in, the analogy of P in our language, and we're using the word projection to describe what this map is doing. It's projecting from this pair the element that came from A, and from this pair the element that came from B. Similarly, in the case of Cartesian coordinates, right? You could have a projection that gives you this value, right? And another projection, pi y, that gives you the y value, right? So pretty simple stuff, but they're important maps, okay? These are morphisms, so to speak, from this product object to the objects that made the product. And notice that the arrows are going from the product object to the object that made the product, okay? Or objects that made the product. Now, as a responsible principal, which you obviously are, you're also going to want a roster of the students. Or an inventory, right? And you're not gonna just group them all together as one group of students, even though they are. What you want is you also want to keep the information of whose class they're in. So we can do exactly that. And I'm going to draw this roster up and then turn it back on. Okay, so here's your roster. And again, I've got what looks like pairs. Okay, I've got one kind of set here, and there's 3 of them, and they all come from A. I've got Amy, Brian, and Carl on the list. And I've got 3 coming from B, Russ, Sophia, and Tom. These are all the kids who are going on the field trip, okay? And so you can notice here for a second, I've got 3 and 3, so I've accounted for all the elements in both sets, okay? And what we're calling this roster is the coproduct. This might be the one that's less familiar, but it's very natural, and I guarantee you've done this in your life at some time. You've probably taken account of things. Maybe you're counting up your assets and you want to add up, well, how much do I have in my house? How much do I have in my bank account? How much do I have in stocks? They're separate sets, right? But you're adding them all together as a net something, right? And you're keeping in mind where they're coming from. Or maybe you have pairs of shoes, different kinds of pairs of shoes. Maybe you have 2 pairs of hiking boots and 2 pairs of running shoes and 2 pairs of dress shoes. They're not the same, They're different, but together they're all shoes, right? And similarly, this is all the students. Okay, together this is A upside down pi B. This is the coproduct of A and B. And they're all students who are assigned to different classes. To different classes. Okay? And we're keeping the information of which class they come from so that we can make this deeper abstraction and stop calling them different classes and start calling them students. Okay? And that's really the idea here. We're increasing our abstraction. Okay? Okay. So this roster describes all the students who are in the class, but also attributes where they came from. And similar to this map here, I'm going to go ahead and take a second to clean this up a little bit. And maybe I'll drag this up in a second. Or you know what, I'll just do it now. Here's what we had for the product. We have something else for the coproduct. Okay? But you'll notice that the arrows on this graph are different from the arrows on the other graph. You have the same, object setup, right? You have the coproduct here, and this would be something like a Amy. But you have arrows coming in. Okay? And so we use the word I, or the letter I, because we're talking about inclusion maps. And remember, pi was a projection map. Okay? And here's how this works. You take an element, Amy, from A, and you say something like, Amy is in the group of students. So Amy is in the group of students and she comes from class A. Similarly, this is IA of Amy. Similarly, you've got Tom is in this group of students and he comes from class B. So this is IB of Tom. And you can think about the difference between IA and IB as being the letter that describes where they come from. Okay? And notice that here I have one object. I have one thing that's going to both A and B. And here I've got something from A and something from B. And they're not really the same. I have a copy coming from A, that's Amy. I have a copy of Tom coming from B. And both of these are represented in this abstraction of a coproduct, which is really just a roster of the students. Okay? So you can think of this as like the list of everything. Now, I'm going to pause it for a second. I'm going to clean this up. We're going to do one more example, and then I'm going to get into the universal property. Okay. So here we have Sally, and Sally likes animals. If you have a daughter, maybe you can relate a little bit. She's got 5 pets that her parents probably take care of. She has 2 dogs, Missy and Puddles. She has 1 parrot, Captain Hook, and she has a cat. She has 2 cats, Carl and Lady. I really like that name, Carl, I guess. So we're going to talk about the coproduct here first, because this is really, I think, in my opinion, the more abstract of the two. The product is pretty simple. You just take one from each set. And I don't think, if you're watching this, you probably don't have much difficulty with the product. More likely you're going to have difficulty with the co-product. So let's think about, let's call this the set D, this the set P, and this the set C. Let's think about what D and C, the co-product of these two, winds up being. So really we're just looking at elements of D, which are the dogs, Missy and Puddle, and elements of C, Carl and Lady. All right, and remember that we're going to map into this. We're going to include all of the elements of D. Okay, and so that's going to give us the following. It's going to give us dogs. Or maybe we'll make this a singular. So dog and Missy, and dog and Puddles. Okay, so we're listing the two dogs that she owns. And then we've also got this inclusion map from C, the cats. So we're going to list the cats as well, and we're going to specify that they're cats. So we have Carl, who's a cat, and we have Lady, who's a cat. Oh, poop. Actually, I think I could do this quickly. Shoop. Just move that to the other side. Okay. And here's our co-product. It's these four items. We've basically just taken an inventory of the dogs and the cats that we have. We've got Missy and Puddles, who are dogs. We've got Carl and Lady, who are cats. Another quick example would be P and C. Okay, so we need an inclusion map coming from P and an inclusion map coming from C. Okay, and so we're going to include everything in P. Well, that's just Parrot, Captain Hook, and then we talk about the cats. We've run out of parrots at this point. There's only one of them. The cats are Carl and Lady. Okay. So let's take a second now to get the gist of what the co-product is doing. And we're going to talk about this a little more abstractly. The idea of the co-product is that we're creating an object that is, quote unquote, the least specific object that every participating set admits a morphism to. Okay, so remember we had this ID morphism and we had this IC morphism. So we have morphisms between D and this object, the co-product, and C in this object. And remember, these were dogs and these were cats. Okay, so we're talking about the least specific object that both admit a morphism to. So here's a good name for this one. This would be dogs and cats. Okay, here's another one. This would be parrots and cats. Okay, here's kind of an interesting one. Let's say I took the co-product of all three of these, and these are all the pets. One way I could say this is dogs and cats and parrots. Another way I could say it is roster of pets. It's just the pets. Okay, so this is the idea. We're abstracting both D and C in this object. Okay, we're combining the two. It's not a union. It's a disjoint union. We're still maintaining that elements that came from the set of dogs are still dogs, and we're maintaining that elements that came from the set of cats are still cats. So that extra, dog on the front is pretty important here. So for instance, if we had a cat named Missy, right? We wouldn't get confused and think Missy the cat was Missy the dog. It's not a union. we are keeping all of the abstraction of D and all of the abstraction of C, and all the specificity of D and all the specificity of C, and we're combining them into a new object. That is what is happening here. Okay, so now we're moving on to what's called the universal property. This is specifically for products. The universal property, it looks freaky right here, so don't look at this for a second. Just close your eyes and listen to me. All this is saying is that the product is very specific and very natural and very basic for what it does. And what does it do? It combines students from Mrs. Adams' class and students from Mr. Bond's class into pairs in a way that you could still separate who's a student in Mrs. Adams' class and who's a student in Mr. Bond's class. That's it. You just have a pair. One of them's from Mrs. Adams' class, and you can always say which one that is. You can pick that one out, and picking that out, that action of picking them out, is pi A, this projection. And similarly, you can pick out the student who's in Mr. Bond's class, and that action is pi B, the projection back into B. Well, what the universal property says is that that product set, is the most natural way to express that. And that if we have another set, X, that does a similar thing, it's related to A times B, the product set, by a unique homomorphism. So in other words, the product set is unique up to what we might call isomorphism for more complicated things. And maybe before I get going on the example, I just want to point this out. This is the same thing as this graph here, okay? So look at these two things. So notice what I've done is I've replaced the product set by X, and that's this triangular thing that you're seeing here. And then I'm just saying, look, if this is true and I can project onto A and I can project onto B from X, then I got to be able to write some morphism here between these two things. That's all I'm saying, okay? So I'm going to do a quick example here. And for the example, I've gone ahead, I've made a simulation of like a bus seating assignment. Okay, so these are the students, and we've assigned each seat on this bus to a student, and this bus is going to take the students to their field trip. And what we're interested in, X, is just the bus assignment of the first row. Okay? That's all we're looking at. It's just the bus assignment of the first row. And F1 is going to be who is seated in the first row from Mrs. Adams' class. And F2 is going to be who is seated in the first row from Mr. Bond's class. You could even generalize this further, and you could actually call X bus assignments, right? You could just say, look, this entire thing, this entire bus assignment is X, okay? Or is an element of X. But I'm going to stick to the first row just to make it easier to draw here. And you'll see very quickly I'm not saying anything new. But when I have my pair here, these are the people who are in the first row. I can see that F is taking whoever's in the first row and calling out the person who's in Mrs. Adams' class. Now, for this to be well defined, it's important to note that the left seat can only be occupied by people in Class A, and the right can only be occupied by people in Class B. There's probably another way to do it where it's still well defined, like you could switch these, or maybe you could mix them up. But one student has to be from each class in the row in order to use this morphism, or these morphisms. So let's ask the question, who is seated in the first row? Well, Amy, Tom. who's also from Mrs. Adams' class? Amy. Okay, who is seated in the first row from Mr. Bond's class? So now we're doing F2 on Amy Tom. And that's Tom, obviously. He's in Mr. Bond's class. So we get Tom. Tom's in B, Amy's in A. Good so far, okay. Now, what could this morphism be? This could just be the identity morphism. It could be, if X was the total seating assignment, it could be who's in the first row, right? And you could return Amy Tom, right? But whatever it is, it's going to map to A times B, and it's going to give us Amy Tom. Okay? And from there, we perform our projections, and we get Amy over here, and we get Tom over here. So what did I just say? Nothing new, really. What I'm emphasizing is that if I have an X, and I have morphisms F1 and F2, where I can take an item from X, and I can peel off a piece of A, and I can peel off a piece of B, I basically have to have some kind of a product. Okay? In other words, I have to have something that's related by morphism to a product. And look at what I started with. I started with a product. Okay? I started with an element of the products, and I just split it up that way. You could do this any way you want, but let's say that I had, let's say for a second that I had something that just returned, let's say I had something that returned just one name in X, or X just had, X was Amy. Okay? Well, then I could write this morphism, but I'd have a hard time writing this morphism, right? Unless this morphism was something like not included. I don't even know if that is a morphism. That'd be kind of an interesting one. But anyway, the bottom line is you have to start with a pair, okay? You have to start with a pair in order to take a piece of it and send it to A, and take a piece of it and send it to B. That's why we say this is the universal property. If I have any X and F1 and F2 that fits this description, it's related to the product in some way. And further, that means that the product is the most basic object that does what I'm describing. Groups together two things, A and B, two classes in this case, classes of students, and also allows me to project back to A and B. Okay, so moving on to the universal property for the coproduct. Very similar. We have this kind of triangular looking construction. Don't freak out. We've got the inclusion maps. Again, we've already seen this part of it, right? This is from earlier when we were talking about a roster of all the children, or coproducts of pets or whatever. And I'm going to do this again because I kind of liked this. Now, the key to this, I don't know if I mentioned this or not. The key to this is that this graph commutes. Okay, and when I say that, I mean that going from here to here is the same thing as going from here to here to here. And similarly, going from A to Y, for instance, is the same thing as going from A into the coproduct and up to Y. It's pretty important. So I probably should have mentioned it, but I didn't, and I'm mentioning it now. But I'm going to do this again, and this doesn't exactly show you what's going on because I'm in no way pointing to the fact that these commute here. But I am showing you that the structure of this is pretty similar to the structure of this. And that's how this triangular graph is sort of built, right? You have what we already saw, where you have an inclusion from A into the coproduct, an inclusion of B into the coproduct, and then you have this object Y that we're comparing it to, and we're trying to make the same case. We're trying to say, look, this coproduct is the most natural, general form of what it does, okay? It specifically is the least... let me rephrase that. It is the least specific object that admits a morphism from A and B. In other words, the disjoint union of A and B, or when we were looking at pets and we were looking at the set of dogs and the set of cats. Well, the disjoint union of cats and dogs, that is defining whether or not they're dogs or cats, and then also including their name, that's the coproduct. It's the least specific thing where I can put an inclusion map from both the dogs and the cats. And I'm just doing the same thing. I'm saying that if I have an object Y that I can include A in and I can include B in, there's got to be some unique morphism coming from the coproduct to Y. Okay, so I'm going to pause this. We're going to come up with an example here. I'm going to use this as an excuse to introduce another example for the coproduct, because to me it's the far more confusing construction. Okay, so here's what I've done. Johnny went birding or bird watching. Okay, and his birding list, the list of birds he saw, which I got surprisingly general on when I got to the genus level. It looks like I'm not including species names, which is a very lazy thing to do, but I don't have that much space, so what are you going to do? He saw some cranes, some egrets, he saw some buntings, finches, some falcons, and some eagles. Okay, now the falcons and the eagles, those are raptors, and the buntings and the finches, those are passerine birds, and the cranes and the egrets, when he got to the lake, I guess, were wading birds. So maybe he went in Central Texas or something like that, or Florida maybe. So we're going to start here. We're going to say, well, let's say A is the passerines, okay, and let's say that B are the raptors, okay. Then we could see in this construction here that this coproduct is going to be the passerines and the raptors listed as such. So we'll have P and bunting. So this is just an inventory of what he saw, kind of including what it was. Finches. Then we have raptors. Oh, and did I say A? Well, I probably should have said A there, but it's okay. I think you know what I mean. I'm going to change it anyway. But so A is the group of passerines, and that includes the buntings and the finches. And then he's got these raptors too. He's got falcons, and he's got eagles. Missed an A there. Okay. So this list, this inventory of all the passerines and raptors that he saw, this is obviously, it's got an inclusion map from A into this set here, and an inclusion map from B to this set here, right? And we're saying, okay, there's another object Y, okay? And Y is a more general object, and I can also include A and B into Y, okay? So what's a more general object I could include this into? Well, I could pick birds, right? And I could make the same map, actually, IA and IB into birds. I could even go more broadly than that and say, like, warm-blooded animals, you know. And I could make Y warm-blooded animals. And I could also make an inclusion map into that, right? I could even make this a subset of things that move. And I could, you know, maybe I'm getting kind of out of hand here, but the point is this. Whatever I choose up here, if I'm including A in it and I'm including B in it in the same sense that I'm doing here, what has to happen? Well, I have to have some kind of an inclusion map from the passerines and the raptors into these objects. So for birds, that's a less specific object than the coproduct is, granted, but it's got a lot of other families in it. It's got wading birds. It's got, maybe he saw some, maybe he saw some thrushes or something like that, although that would be a passerine. My point is, it doesn't admit a morphism from, those groups don't admit morphisms from A and B. And these are all the morphisms you have from these two families, A and B, are going to be found here. So what I'm doing is I'm just finding more general things, more general ways to describe what I've already kind of described in a pretty concise way. And that's what I mean. I'm going to do another example here in case that one wasn't clear. Okay, so I've got a pretty good one for you here, and I think this might take a couple of takes, so bear with me. Let's say Johnny, on his way to go see the birds, okay? He flew from Australia or something like that, okay? So Johnny flew from Australia, and on the way to the U.S., he flew first class. Okay? So he got to sit in a first class seat on the way to the U.S. Okay? But then he had like a little, puddle jumper type thing. He had to go from, like, let's say he was going to Florida. He had to fly into Atlanta first. So he had a little regional flight. And he said, well, I just flew first class from Australia. That's a pretty pricey ticket. So I'm gonna go coach this go around. So now he flies coach. Okay? And he gets to Florida. Now he takes a train. But he decides to splurge again. So he goes for the first class cabin. And I'll say airplane seat. Coach airplane seat. He takes a train and he goes first class. Then he rents a car. He rents a Honda Civic. Okay? So he sits in a Honda Civic seat. And then he goes to his hotel and he gets an okay hotel, but he has to wait a little bit in the lobby, so he also sits in the hotel lobby seat. Okay? And, he looks back on his trip and he realizes that the first class seats are far more comfortable. Okay? Ugh. I'm just going to write comfy. When you get into the table, it gets real ugly. I'm going to try to do this in one take. So forgive me if I screw it up. I'm just going to keep on plowing through. So this seat was comfy. And this seat was comfy. Right? So let's think about this. Johnny, he's kind of I don't know, he might be a programmer or something like that. He's into category theory. He thinks it's kind of fun. So he's going to sit there and he's going to think about the co-product of some of the things that he's experienced so far before he gets to go birding tomorrow. So he starts thinking about his seats and he thinks, wow, I got to go on 2 airplanes, right? And I got to go on a train. Right? And so what I'm going to think about is I'm going to call the set A. I'm going to call the set A the first class seats that I took. Okay, so what are those? Well, I took a first class airplane seat, and I took a first class train seat. Okay? And then I also took a coach. I also took a coach airplane seat. Okay? And so we're going to think about this. What's the coproduct of A and B here? Well, I could call it airplane and train seats taken. right? Because that's what it is. I mean, he's covered everything. You could call it something else too. You could call it like all the trans, the non automobile seats taken, or something of that sort, right? And of course, this is. You could also say that A and B are both inside the seats taken while traveling. Right? And you could include A in this co-product and B in this co-product, as we've already done. These are the first class seats and the coach seats. But you could also include these in this less specific group, this less specific set, I should say, of all the seats that he took while he was traveling. And even further, right? I could include this in all the seats he took while he was away from home. Seats away from home. Right? But notice that at each point I've got kind of an inclusion map here, right? These are included in these are included in these. And the most basic way to put this is the airplane and train seats taken. Let's think of, is there a more basic way to put the disjoint union of A and B? There's not. I could also write this as, let's think of another one. Let's think of comfy seats. Let's say the hotel lobby was a comfy seat. Right? And I'll get rid of all this nonsense up here. Yeah, this could actually be fun. So here's the hotel lobby, the comfy seats, okay? Okay, these are going to be the hotel lobby. The hotel lobby seat, the first class train seat, and the first class airplane seat. Right? And in each of these we have that these are comfy. So that you'd have a pair that says that these are comfy, and that it includes the hotel lobby seat, the first class train seat, and the first class airplane seat. We could also say seats in a car. Or even further, we could say traveling seats, right? Travel seats. This is such a stupid example. Okay? It's inspired actually by a much better example that was written in this book, Category Theory for the Sciences. So I'm kind of stealing this, but I'm trying not to by making it completely stupid to go with the title of the whole video. I am, after all, an idiot. So the travel seats would include the first class train seat, the first class plane seat, the Honda seat, and the coach plane seat. And notice what I'm doing here, right? I'm making copies of these, but I'm still going to have to state that they're part of different sets. So when I have my disjoint union here, I'm going to have A, hotel lobby, A, first class train, A, first class airplane. But I don't combine, when I combine it with B in the co-product, I still delineate between the two. I make a distinction between the two. So I have B first class train, right? So that's two copies of first class train. B first class plane, B, Honda, and B, Coach. Plain. Okay? This again would be included in all the seats taken. But if there is a map, and that map would somehow map these two things to the same thing, right? And these two things to the same thing, it would include everything in this coproduct. In other words, this coproduct would remain the least specific thing that has a morphism between A and B. And anything that I created off of this would have to have something else in it that kind of wasn't completely faithful to a specific copy of A and a specific copy of B. I hope that that is clear. The last thing I'm going to do here is put both of these maps up right next to each other, and you'll see why we call these dual properties. Okay, here's the last little bit here. Here we have the universal property construction for the product, and here we have the universal property construction for the coproduct. And you can see these look very similar in structure, but all the arrows are reversed. And that's a really general way of saying that these are dual properties. These are dual. Okay? Thanks so much for watching.